Today we will start with ideal and non-ideal solution. So, our topic ideal and non-ideal solutions. So, what exactly are ideal solutions? Ideal solutions basically are those solutions which obey Raoult's law under all conditions of temperature and concentration. So, we say that obeying Raoult's law under all conditions of temperature and concentration. So, coming back to what is Raoult's law, all of us have already studied what is Raoult's law. So, according to Raoult's law, we had said that the vapor pressure of any component, that is the partial vapor pressure, is directly proportional to the mole fraction of the component in the solution. Mole fraction x or zeta, or in other words, mole P is directly proportional to x, or P is equal to P naught into x, where P naught is the vapor pressure of the component in the pure state. For example, if we consider a solution made up of different components. For example, we have different components A and B. Now, this is enclosed. Each of these components have their own vapor pressure under different temperatures. So, the vapor pressure of each of the component that exists individually with that particular component will contribute to the vapor pressure of the component in the pure state. So, according to Dalton's law of partial pressure, from Dalton's law of partial pressure, the total pressure P will be equal to PA plus PB for the two components A and B. If there are more number of components, it will be equal to PC and so on. So, based on Raoult's law, we define our ideal and non-ideal solutions. Coming back to what exactly is an ideal solution. Ideal solution we have defined as those solutions which obey Raoult's law under all conditions of temperature and concentration. So, a few factors we must know in order to study what exactly is an ideal or a non-ideal behavior. For example, we introduce a few terms. Delta V mix. This means the volume of mixing when the solution is formed. Another term, delta H mix, the change in the enthalpy of the mixture, that is when the solution is formed. And most important of all, the intermolecular forces that exist between the components. For example, if we have two components, this is component A having a volume V1, these are the particles of A, another component B having a volume V2, when these two get mixed together, what exactly will happen? Will the volume remain the same? Will the volume increase or will the volume decrease? Normally, we would always say, with your previous knowledge, you would say that the volume would always remain the same. But ideally, always it does not remain the same. We have deviations, so volume can remain the same. When the volume remains the same, the volume will become V1 plus V2. This is the final volume which will have all the particles of both the components present in it. If both the volumes V1 and V2 is equal to the final volume exactly the same, in that case there is no change in volume before and after. That means there is no loss of any of the volume anywhere. In that case, we say that delta V mix is equal to 0. The change in volume remains the same, the volume does not change. That is V1 plus V2 gives us V final. Secondly, delta H mixing. When the volume is added up, when V1, component V1 and V2 are getting mixed together, is there any change in the enthalpy? Is heat getting absorbed or is heat getting evolved? What exactly is happening? That tells us about delta H mix. In this particular case, these changes in volume or changes in the enthalpy are totally based on the intermolecular forces that are present between the components within A itself, also between the components B and B. A and A, they have their own interparticle forces, B and B have their own interparticle forces. When A and B combine, that means A and A forces have to be broken, B and B forces have to be broken. To break the forces, we supply an extra energy. Energy is required, and when these forces are broken, they combine together to form the solution molecules AB. And when a molecule is formed, when formation of the compound formed or when solution formation takes place, energy is released. So, in this case, if the energy absorbed during the breakage of AA components, BB particles is the same as the energy of A and B after forming the solution, then the solution will have no change in enthalpy, delta H is said to be 0. That means what have we learned so far? We have seen that main conditions required, delta V mix, we should know what is delta V mix, change in the volume after mixing, change in the enthalpy delta H after mixing, how and all the intermolecular forces are involved during the formation of the particular solution. In this case, we have seen if the volume of mix is 0, if the volume of enthalpy mix is also equal to 0, then in that case, if this is equal to 0, delta H mix is also equal to 0, AA intermolecular forces and BB intermolecular forces are the same as A and B intermolecular forces, then in this case also ideal conditions are applied. In that case, there is no change in volume, volume mix is 0, delta H mix is 0, then we get another situation. Then in that case, our Raoult's law where what we have applied, PA equals to P naught A zeta A, PB equals to P naught B zeta B, total pressure P will be equal to P total will be equal to PA plus PB. So, the conditions that are required for any solution to be ideal will be delta V mix should be equal to 0, delta H mix should also be equal to 0, PA will be equal to P naught A x A, PB will be equal to P naught B x B, that is total pressure P will be equal to PA plus PB. In such conditions, when all the three conditions are available to us, then we say the solution obeys Raoult's law, and then the solution is said to be an ideal solution. Now for ideal solution, if we study what exactly the graph looks like. Can I rub this? Yeah. We plot a graph of the vapor pressure against the mole fraction. Vapor pressure, and here we have the mole fraction. Our two components, the mole fractions. In the first case, we are considering XA is equal to 1 xb is equal to 0 and over here xa is equal to 0 and xb is equal to 1. We know that sum of the mole fractions cannot be more than 1. So, for A, when xa is equal to 1, we know that Pa is equal to P naught A xa. So, when xa will be equal to 1, xa is equal to 1 here. So, P naught A will start because xb is 0 over here. The graph will be moving over here along this line and here we have P naught A. This is the vapor pressure of the pure component along this axis xa. Similarly, when xb is equal to 1, starting from 0 here because xb is 0 over here, the vapor pressure of the pure component B in this case here it will be P naught B. So, this line is for Pa is equal to P naught A xa. This is for Pb which is equal to P naught B xb. The total pressure at any point on the graph, at any point here, total pressure P total will be equal to Pa plus Pb. So, over here xa is 1, its mole fraction. So, it has a pure component, vapor pressure of the pure component is P naught A. Over here the vapor pressure of the pure component is P naught B because B is equal to 1. A is 0 over here, B is 0 over here. This is an ideal condition for any solution which obeys Raoult's law. Now, according to this graph, we also see, is it practical that any solution can behave as an ideal solution? Yes, a few solutions under certain conditions do behave as ideal solutions. What is the condition required here? The required condition for any solution to be ideal is at low concentration. That means if the concentration is low, the solution has to be very dilute. When the solution is very dilute, the two components that are combining to form the solution, if they are of almost the same polarity and almost similar structures, then they would form ideal solutions. Our examples over here for ideal solutions can be N-hexane and N-heptane. Another example, benzene and toluene. So, we can consider many examples taking together their similar polarity, either they become same polar, non-polar or polar, and they should be almost of similar sizes. So, these are two main examples which show ideal behavior. So, those compounds or those substances which behave Raoult's law under similar conditions, that is all conditions of temperature and concentration, they exhibit ideal conditions or they are called ideal solutions. For example, for ideal solutions, delta V mix is 0, delta H mix is 0, the intermolecular forces between AA and BB is almost equal to AB. Why I said pressure is not correct? Because we are not considering gases over here. It is with respect to solutions. So, because we are considering solutions, we are taking into consideration the concentration as well as the temperature. Now, coming to what exactly are non-ideal solutions. So, once again ideal solution, for an ideal solution delta V mix is equal to 0, delta H mix is equal to 0. We have Pa is equal to P naught A xa, Pb is equal to P naught B xb and P total is equal to Pa plus Pb. So, this was our ideal condition for ideal solution. So, now what exactly are non-ideal solutions? Can I rub this? Okay. For non-ideal solutions, also we consider the same factors, delta V mix, delta H mix as well as the intermolecular forces. What would happen in non-ideal conditions? We had said when the molecules or the intermolecular forces before and after combining remains the same, the volume is not changing. Enthalpy change is not taking place. So, in this case volume may change, volume will change, but for change in volume there can be volume greater than existing volume, volume lesser than the existing volume. So, we have two possibilities. Based on these two possibilities, non-ideal solutions are those solutions, they are of two types. Non-ideal solutions, one which show positive deviations from Raoult's law, and second, non-ideal solutions which show negative deviations from Raoult's law. So, two different conditions we have here for non-ideal solutions, those which show positive deviations from Raoult's law and those which show negative deviations from Raoult's law. Let us consider the first one, non-ideal solutions showing positive deviation from Raoult's law. For solutions containing positive deviations from Raoult's law, positive deviation means the volume should be greater. Whose volume? Delta V mix should be greater, enthalpy delta H mix also should be greater. So, we have two conditions here, delta V mix, this should be positive, delta H mix, this also should be positive. Both these conditions again depend on our intermolecular forces. So, if we go back to our diagram of the two components that are combining together, this is component A, it has its own particles, this is component B, this has its own different particles, this is B, this is A, this is having volume V1, this is having a volume V2. We are discussing non-ideal condition showing positive deviations from Raoult's law. Now, when these two combine, this is our ideal condition of both V1 and V2, but when it shows positive deviation, it is found that V1 plus V2 comes over here. The molecules are all separated away from one another. The volume has increased. This is V final. Delta V mix is said to be positive. It is greater than 0. Why exactly the volume or the molecules are separating? That means the partial pressure or the vapor pressure of the components is much higher over here. Vapor pressure is increasing, molecules are far apart. When we consider delta H mix, this also is found to be positive. Why is it positive? If we see the intermolecular forces that are taking place here. Here again we notice that AA intermolecular forces, this is BB intermolecular forces, and finally they are forming the solution A and B. In case of this, because these particles are far apart from one another, the AB intermolecular forces are much less than these two AA and BB forces, they are greater than A and B forces. A and B is less than AA particular forces, interparticle forces, and BB interparticle forces. We require energy to break this, we require energy to break this. But the bond that is formed between A and B, that is the solution that is formed between A and B components, the molecules are far apart from one another. We are seeing that particle forces are broken here, energy is supplied, this is formed here. But the resultant solution that is formed is having a final volume, that means the forces over there are much lesser, that is why the vapor pressure is higher. So, in this case, as the vapor pressure is higher, due to less stability, delta H mix becomes greater than 0 or is said to be positive. So, intermolecular forces in this case we have finally said for A and B is less than AA and BB. Examples in this case we can consider solutions between those components. One component may have a hydrogen bond, the other not having a hydrogen bond. For example, we can take examples of ethyl alcohol and cyclohexane. Ethyl alcohol and cyclohexane will be good examples for deviation, showing positive deviation through Raoult's law. The graph for this we can also show it in a similar manner and then conclude from the graph. We first draw the graph for an ideal behavior. XA is equal to 1, XB is equal to 0. It is the same graph, vapor pressure against mole fraction. Here XB is equal to 1 and XA is equal to 0. This is P naught A, this is P naught B. Now whatever I am drawing the ideal conditions. For ideal gas equation, I am representing it with a broken line. The total pressure P, this was P total equal to PA plus PB. This was PA and this was PB. Now because our conditions delta V mix is positive, delta H mix is positive, then we have PA is greater than P naught A XA, PB is greater than P naught B XB, and P total is greater than PA plus PB. So seeing all these conditions, we find that because PA is greater than P naught A, this is the ideal condition, there will be a small increase in the volume over here, as well as the temperature. There will be a small increase over here for the vapor pressure. Vapor pressure is increasing because there was an increase in the volume due to the far position of the particles of both the components, and P total will also be increasing over here. Compared to the ideal behavior, this was the ideal, V ideal, and this shows positive deviation. The curves on the top, P total, this is for PA, this is for PB, and this curve is for P total. That means compared to the ideal behavior, we notice that there is an increase in the vapor pressure because the molecules are far apart. We can see it from the normal graph, from the ideal graph, the difference, what exactly is taking place between ideal behavior for an ideal solution as well as for that solution which is showing positive deviation from Raoult's law. So for positive deviation, delta V mix is greater than 0 or is positive, delta H mix is positive, the intermolecular forces, that is P is greater than P naught A XA, PB is greater than P naught B XB, and P total is greater than this, as the intermolecular forces between AA and BB are greater than AB intermolecular forces. AB molecules are far apart. So as a result, because the molecules are far apart, the vapor pressure is high. The molecules are not bound together. In this case, at any one point we see that at any one point the vapor pressure of that component becomes very high. We will later refer to what these components are called at that particular point. They are called isotropic mixtures. We will discuss it in our next class. Next we come to what are non-ideal solutions showing negative deviation from Raoult's law. So can I rub this? Okay. For non-ideal solutions showing negative deviations from Raoult's law, again we come to the same condition. For a solution of component A, the molecules, the particles, component B, this is A having volume V1, this is component B having a volume V2, this has different particles. When they combine, we are discussing negative deviation from Raoult's law. If the ideal behavior or the ideal solution is V1 plus V2 is here V ideal, in this case it is found that it is much less than V ideal. V1 plus V2 will be less than V ideal. The molecules will be very close to one another. Molecules are coming closer to one another. So what is happening over here? The volume is, because the molecules are coming closer to one another, the partial pressure or the vapor pressure will decrease. So delta H mix will become negative or will be negative or less than 0. Delta V mix is negative, delta H mix also is negative. The intermolecular forces between AA and between BB are much less than intermolecular forces AB. Here AB molecular forces are much greater than AA and BB intermolecular forces. Because the intermolecular forces of A and B are greater, the molecules in the solution form, the components, the particles are coming much closer to one another. As a result, the vapor pressure of the solution is decreasing. So when the vapor pressure decreases, now because the particles are coming closer and when a bond is, stronger bond is formed, there is a decrease in the energy of the system. The component is becoming, the solution is becoming more stable, there is a decrease in the energy of the system, delta H decreases, intermolecular forces AA and BB are less than AB. So as a result, because the volume is decreasing, delta V mix is negative, delta H mix is negative, PA in this case becomes less than P naught A XA, PB becomes less than P naught B XB, P total becomes less than PA plus PB in this case. So and the graph for this exactly similar to the one we have drawn for the positive deviation, only that because the volume is decreasing, the deviations will be towards the lower side of the ideal behavior. So we have vapor pressure, mole fraction on this side, XA is equal to 1, XB is equal to 0, XB is equal to 1 and XA is equal to 0. For an ideal condition, this is PA because this is P naught A, this is P naught B, this is PB and this is our total pressure. P total is equal to PA plus PB. For a non-ideal condition showing negative deviation from Raoult's law, because the volume is decreasing or delta V mix is negative, delta H mix is negative, we will have the curve slightly below the vapor pressures here will be in this way. So this is the ideal behavior and this behavior shows negative deviation from Raoult's law. So which are the compounds or the components which show negative deviation from Raoult's law? Because the volume is decreasing, we can take many examples. We have a number of components wherein which we can show that suppose the two components have got combining have got hydrogen bonds between them. We can show examples between chloroform CHCl3, C, Cl, Cl, Cl and H plus acetone C double bond O, CH3 and CH3. In this case, this tries to bring the electron more towards itself, this pulls the electron from hydrogen and hydrogen finally pulls the electron from this oxygen over here. Oxygen gives the electrons to hydrogen. So, bonds are formed here. A hydrogen bond is formed between hydrogen and oxygen of each of the component. So, in this case hydrogen bonds are formed. As a result, the molecular bond is becoming, the components are becoming stronger, and the bond, that because it is becoming a stronger bond, we see that there is a negative deviation from Raoult's law. We can use many other examples like acids plus water. Strong acids, when they combine with water, they also show negative deviations towards Raoult's law. But in case of positive deviations, we have seen that if one component is showing hydrogen bonding, the other component which is combining with it is breaking the hydrogen bond, and that is why the volume is increasing. In this case, the volume is decreasing. So, this shows, so finally we get, in case of negative deviation from Raoult's law, delta V mix is negative, that is less than 0, delta H mix is also negative. The intermolecular forces, AB molecular forces are greater than AA and BB. PA is less than P naught A XA, PB is less than P naught B XB, and PT is less than P naught A, because there is a decrease in volume as well as the enthalpy of heat, delta H of enthalpy in mixing. So, according to this, finally we get what are ideal solutions, those which behave go according to Raoult's law, that is under all conditions of concentration and temperature, and these are changing with respect to concentration and temperature, are the non-ideal solutions. Thank you.